know, this relation between stationary spacetimes, classical stationary spacetimes, and Brandeis metrics. In a third part, I will speak about the Zermelo problem of navigation, which is also related to Brandeis metrics and stationary spacetimes. And finally, I will discuss the wildfire spread modeling applications, which is related also with Huygens principles. So, well, I want to begin with the concept of norm in analysis, which probably everybody knows. And, well, there are usually three properties. It has to be homogeneous, and this is related to the fact that the length of a curve does not depend on reparameterization, only on the path of the curve when computed with the norm. Then, well, it has to be positive in the sense that it is zero, even only if the vector is zero. And then we usually require to satisfy the triangle inequality. Okay, so let us focus a little bit in the triangle inequality. Okay, and well, I'm going to define the indicatrix, which is the vectors where the norm is equal to 1, and the unit ball, which are the vectors with norm less or equal to 1. Okay, so the first proposition that we can establish, imagine that we don't require to the norm to satisfy the triangle inequality. You can prove that the unit ball is convex if and only if the norm satisfies the triangle inequality. Okay, the proof is very simple. I don't have a long time here, so but yes, you have to see that if this is convex, then there is a certain convex combination in such a way that it has, because it's convex, it has to be in the unit ball, and then this implies the triangle inequality. Okay, and the other implication is also very, very simple. But well, this fact is very important. The unit ball is the convexity of the unit ball is equivalent to the triangle inequality of the norm. Okay, so well, really, the norms that we will use in Finsler geometry are Minkowski norms. And there are several differences. Okay, the first one, now I'm going to consider an arbitrary vector space of finite dimension. Here I'm going to consider only vector spaces of finite dimension. So, well, the first thing is that F, this Minkowski norm, has to be smooth away from the zero section. In analysis, you don't require the norm to be smooth, but here it has to be, and you will see why. Well, the second condition is the same one as in analysis. The third condition is positive homogeneity of degree 1. In this case, we don't require the homogeneity, just positive homogeneity. Yeah, because, well, you can think that you want to compute the length of curves, and well, you are interested in the reparameterizations in one sense. If you reparameterize in the opposite, it's another path, let's say. Okay, and there are also very interesting examples which are not homogeneous, but only positive homogeneous. Okay, and the fourth property is that, well, basically the fundamental tensor of F, which is defined as 1/2 of the deviation of the square of F, is here. This has to be positive definite. This quantity is very important. It's fundamental, and this is the reason because I call it the fundamental tensor. And this gives you a scalar product in every direction. Okay, it's like, well, now we have a Minkowski norm, and this Minkowski norm produces a scalar product in every direction. So everything depends on the direction. Okay. Okay. A very important thing. Well, here basically we have replaced the triangle inequality of the norm of analysis with this condition, which means that the fundamental tensor has to be positive definite. Okay, let's explore a little bit more the properties of the fundamental tensor. Okay, so as I said, you can think in this fundamental tensor as a scalar product in every direction. Then when you define the indicatrix, there is a very strong relation between the fundamental tensor and the indicatrix. Let's explain this better. Well, we have this formula, these two formulas, which basically these formulas are obtained because of the homogeneity of the Minkowski norm F. Okay, then the first formula, this formula here, implies in particular that V and the tangent space to the indicatrix are GV orthogonal. Yes, applying this because in the indicatrix F is constant and the differential has to be 0. Okay. Moreover, GV restricted to the tangent space to the indicatrix is the second fundamental form of sigma. So at the end, the indicatrix contains all the geometric information of the Minkowski norm. Okay. So let us give more details of this relation. No? The fact that the fundamental tensor restricted to the tangent space to the indicatrix is the second fundamental form of sigma. So, well, let us recall the notion of second fundamental form of a hypersurface. Okay. Well, this second fundamental form depends on a transverse vector psi. Okay. So basically, for every transverse psi, we obtain a second fundamental form sigma psi. Okay, and this second fundamental form is determined by this relation here. Okay, this relation, where nabla 0 is the affine connection of the vector space V. Okay. Affine connection means that is the Levy-Chip, the connection of the Euclidean space, if you want. So, well, this connection can be decomposed in a tangent part to the indicatrix, which is the induced connection, and then a proportional part to psi. And the factor of proportionality is exactly the factor of proportionality. It is the second fundamental form. Okay, in principle, this depends on the transverse direction. Okay, so you can prove that the fundamental tensor GV restricted to the indicatrix coincides with the second fundamental form of the indicatrix when you consider psi the opposite to the position vector. Okay. Well, I think that this was a well-known fact, but it is not easy to find a proof of this, even if it is not very difficult. But you can find a proof here in this paper that I will refer to several times in collaboration with Miguel Sanchez. So for next citations, I will use Jackson 14. Okay. So, well, so what happens when you consider another transverse vector? What happens is that you obtain a different second fundamental form, but it's proportional to the first one. Why? Because if you consider another transversal vector rho, then you can express psi as a combination of a proportional part to rho and a tangent part to the hypersurface. P is tangent to the hypersurface. Okay, so making use of this relation here, this it's gonna give two terms. One is tangent to the hypersurface, and the other one is proportional to rho. So here we have a tangent part to the hypersurface and then a proportional part to rho. So the second fundamental form is exactly this part here. Okay, this part here. So the second fundamental form associated with the transversal vector rho is just lambda times sigma psi in xy. It's proportional to the first one. Consequences of this. Well, you can consider. We know that we are assuming that in the Minkowski norm the fundamental tensor is positive definite. So, and we know that it is the second fundamental form associated with the transversal vector. So when we consider the Euclidean orthogonal vector, which basically when you consider the orthogonal vector to the surface, you obtain the Euclidean second fundamental form, but it's proportional, so it has to be positive definite, or well, definite, maybe because lambda can be negative, but it is definite. So what we deduce is that sigma, the indicatrix, has positive curvature. Because its second Euclidean second fundamental form is definite. Okay. So, well, the conclusion is that the unit ball is convex. And if the unit ball is convex, we recover the triangle inequality. Okay. So, well, in fact, we can claim that the positive definiteness of the fundamental tensor is equivalent to the strong convexity of the indicatrix. Okay. And we can, well, this proposition is very important for the rest of the talk and maybe of the mini-course. Okay. If you want to define a Minkowski norm, you only need to fix a compact strongly convex hypersurface. Compact strongly convex means that the curvature as a Euclidean hypersurface is positive. Okay. Well, it has to be diffeomorphic to a sphere and to a sphere, and then has to contain the zero vector inside the bounded part. Basically, you need a kind of egg which contains the zero vector. Okay, so to define a Minkowski norm is the same thing as to have this egg with the zero inside. Okay. Well, then when we have a Minkowski norm, we also have the fundamental inequality, which is, let's say, a generalization of Cauchy-Schwarz inequality. Okay, and in the same way, the equality is attained if and only if V and W are proportional. You can find a very nice proof of this in a book by Zhongming Shen, Lectures on Finsler Geometry. I don't have time here to make this proof, but it's really very geometric and very nice. Okay, so let's go to the indefinite realm. So now we are going to define a pseudo-Minkowski norm, in such a way that now we don't consider, well, I'm going to name the function L rather than F, and this function is going to be positive homogeneous of degree 2. It's like you are going to consider the square of F, okay? This is because, well, as you probably know very well Lorentzian geometry, and if you consider the square root of GVV, there are problems because GVV can be positive and negative. Okay, so we consider a function which is positive homogeneous of degree 2, and well, now the fundamental tensor is only non-degenerate, doesn't have to be positive definite. Well, the domain of definition, this A, is does not contain, well, here. Here the function is smooth only away from zero. Okay, this is the important thing, and this subset is conic. Let's say this is the same. I'm saying that if V belongs to A, then for every lambda positive, lambda V also belongs to A. Okay, it's very intuitive. So now we are ready to go to manifolds. Okay, we have defined all the concepts in a vector space level. Now we can go to a manifold. M is a manifold. Pi denotes the natural projection from the tangent bundle Tn to M. We will consider a conic open subset. A is a conic open subset. Now I'm going to consider that A does not intersect the zero section. Okay, and it is conic, the same definition of conic. Okay, so our function is going to be defined here in A, in this subset A, is smooth because we are excluding the zero section. Okay, because in the zero section cannot be smooth if it is not semi-Riemannian. So it is a smooth function. Here, sorry, because there's a mistake. This is not 0 plus infinity, is R. Okay. So it is positive homogeneous of degree 2. And then, well, we have a fundamental tensor, which is non-degenerate. Basically, here, what we have is at every tangent space, we have a pseudo Minkowski norm. Okay. And this is done in a smooth way. Okay. Okay, so we have the concept of pseudo Finsler metrics. So just to cite several important cases, well, if we have a semi-Riemannian manifold, then we can define a pseudo Finsler metric just like L, defining L on V equal to GV. Okay. Another important case is when we consider the classical Finsler metrics, which is to consider the subset of definition is the whole tangent bundle. Well, in the 0 section will be 0, okay? But here I remove the 0 section because it is not smooth, okay? Well, in this case, to have a classical Finsler metric, the fundamental tensor has to be positive definite. And well, usually we consider the square root of L because F has to be homogeneous of degree 1, positive homogeneous of degree 1. Okay, this is the what is called classically a Finsler metric. Then we can consider Lorentz Finsler metrics. The particular thing here is that the fundamental tensor has index 1 or n minus 1. Okay. Well, with this, in this setting, we will define Lorentz Finsler metrics. There are several subtleties, and I will discuss these subtleties in the third talk because there are different ways to define what is a Finsler spacetime. But probably this fact that the fundamental tensor has index 1 is common to all the definitions. Okay, so why are so important, for me at least, the Finsler metrics? Well, because this is Finsler metrics provide the most general way to define the length of a curve in a smooth setting. Of course, how do you define the length of a curve? It's very simple. If f is the Finsler metric, then in this case f is homogeneous of degree 1. Okay, so you can define the length in this way, just the integral of f in the derivative of gamma. Okay, so this is the length. This does not depend on the parameterization, and of course is everything done in a smooth way. Then, if there is an isotropy, you will have to consider Finsler metrics because Riemannian metrics locally in the tangent space are very, very isotropic. You can find a frame where the indicative is the sphere. There are many local isotropies, isometries. Also, it's very, there have been very important geometries that have worked in Finsler geometries. Henry Cartan, Schern, Bussmann, and many others. And finally, I want to stress that there are many applications to the real world, and we will discuss several of them here. There are many applications. I don't want to spend much time speaking about them, but basically here we will concentrate in the wildfire spread modeling, which is, I think, that can be a very, very nice application with real impact. And well, Zermelo navigation problem, also I will discuss this in the talk. Matsumoto metrics, which are used also in the wildfire spread modeling. Matsumoto metrics are metrics which search for the trajectories that the minimized time in the presence of a slope, because when you go up, you go slower than when you go down. Okay, if you take this into account, the trajectory that minimizes time is not the geodesic of the surface, okay, of the mountain. You have is the geodesic of Matsumoto metric. But in a wildfire, it is the opposite. The fire goes up faster than it goes down. Okay. So, well, let us discuss the main elements of Finsler metrics, and these elements are, well, in first place, there is a distance, a non-symmetric distance associated, which is computed just as the infimum of the length of the curve between 2 points, two given points, P and Q. Then you can compute. This is the distance is really very important, because in many applications, what you are interested in is in the distance, in searching for the trajectories that attain this distance. So, well, then you can define the geodesics, and the geodesics can be defined as critical points of the energy functional, but they also locally attain the infimum of the distance. Okay, they also attain the distance, let's say, in the positive definite case, of course. In the Lorentzian case, they will maximize the separation or distance. Okay, so now I don't want to enter to give a definition of geodesy with connections, and this will be done in the second session, but just an idea. They are maximized, but you can prove, just analyzing the differential equations, that if you fix the initial velocity, then there is a unique geodesic, okay, that I denote here gamma v, in such a way that the velocity in zero is v. Okay, and finally, this so for every direction you have a unique geodesic up to the parameterizations. So finally, there is another very important quantity. It is the Flach curvature, which is a measure of how geodesics departing from the same point and in the plane VW get apart from the initial one gamma v. Okay, so this is the Flach curvature does not depend only on the plane, but the first, let's say the Flach pole is very important. This is the reason, because they are called Flach curvature. Okay, because there is a Flach pole. It's not it does not depend only on the plane, but on the Flach pole first, and then on the Flach, which is W. Okay. So we will discuss with more details geodesic and Flach curvature in the second talk tomorrow. Okay, so let's go to the second part. In this second part, the first thing I have to do is to define Brandeis Methods, which is a very important example of Finsler metrics. And these metrics are defined as the norm of a Riemannian metric plus a one form. And well, the first thing is that I want to define a classical Finsler metric, so this has to be positive. If I want this to be positive, the norm of the one form has to be H norm of the one form has to be less than 1. Okay, and well, this metric is non-reversible, because when you put minus v here, there is a minus, but it is different from the value of f on v, so it is non-reversible. It is a good reason to consider positive homogeneity rather than homogeneity. Okay, because otherwise you would exclude these Brandeis metrics. And well, a very surprising thing is that this condition, that the one form, the norm of the one form is less than 1, guarantees that the fundamental tensor is positive definite. And there are several ways to check this, but one way is to compute the fundamental tensor. And this is done here in Javaloyes 14. And well, the expression of the fundamental tensor is this one. And if you look carefully to this expression, this term is positive because this is a square. Here, this term is also positive because Cauchy's Barré inequality for the Riemannian metric H, so it's also positive. And well, if this is positive, which is positive by a hypothesis, because I'm assuming that the norm, the H norm of omega is less than 1, then the fundamental tensor is positive there. Okay. So this is a direct proof of this fact. Okay, so Brandeis Methods were named after the Norwegian physicist Gunnar Brandeis, but he was interested in relativity, so he considered H, this H here was a Lorentzian metric, but now in our approach, H will be Riemannian. And in many works in Finsler geometry in the last years, not all of them, but in many of them, H is going to be Riemannian. Okay, it's like a very important case in Brandeis metrics. So let's go to the relation between Brandeis metrics and stationary spacetimes. Okay. Well, the stationary spacetimes is a class very well known, and well, basically they are in a standard stationary spacetime we have a splitting in this way R times S, and well, the main property of this splitting is that if t is the first coordinate, the partial with respect to t is a time-like Killing vector field, and the slice is space-like. So you always can write the metric, write down the metric in this way. So, well, you have this particular, where G0 is a Riemannian metric on S, and omega is a one form on S. Beta is a positive function on S. Okay. So, well, how do we find the Brandeis metrics associated with this stationary spacetimes? Well, we have to apply the relativistic principle. This principle says the following: Lightly geodesics are critical points of the rival time function corresponding to a certain observer. Well, considering a suitable class of Lightly curves. Okay, so well, in this case, we are going to consider, well, you can be smooth Lightly curves if you want. Then the observer in this case, we are going to consider this the vertical line, which is the integral line of the of the Killing vector field. In particular, it is this one here. This is the observer. Then, given any Lightly curve, we can compute explicitly the arrival time, and the arrival time is given by this relation here. Okay, it's given by this relation. So the arrival time up to a constant. This is a constant. It is the length of x computed with a Finsler metric. Well, just why how can we obtain this formula here? It is very easy. It is very easy because, well, we are assuming that gamma is a Lightly curve. By definition, a Lightly curve satisfies this equation here. Okay, satisfies this equation. And well, this is a second order equation in T dot. You can solve T dot and then integrate, and then you obtain this formula here. Okay, so at the end, it turns out that we can define this Finsler metric here. This is a Brandeis metric because, I mean, this is a certain Riemannian metric. It's not G0, but it's well, it is for sure it is Riemannian, and this is a one form. So this is a Brandeis metric, and well, it is easy to check that the norm of this one form is less than one with respect to this metric. Although you can see directly that this addition is positive. This is very easy to see, and it is equivalent to see that the H norm of this one form is less than one. Okay, so this is a Brandeis metric. The important thing is that this is a Brandeis metric. Okay, and well, we can establish a relation between the causality of the stationary spacetimes and Brandeis metrics. This is done in this paper that I'm going to refer to as CJS 11. And well, how can we do all of this? How can we obtain this relation? How can we describe the causality of the stationary spacetime using this Fermat metric? Well, because given a smooth curve in the base in S, then we can define T of S, this function, as the length of x in the interval S. Then this curve here, gamma of S equal to T of S, x of S, is a Lightly curve. It's a Lightly curve of the stationary spacetime. Okay, so given any curve in S, we can lead this curve to a Lightly curve. And moreover, because of the Fermat principle, which is the key point here, gamma is a likely pregeodesic. It's a likely pregeodesic if and only if x is a pregeodesic of the Fermat metric. Okay. So at the end, with these relations, it turns out that you can describe all the causality steps of the stationary spacetimes in terms of completeness properties of F and its associated distance. So let us be more precise. Well, D will be, we will denote by D the non-symmetric distance in N's associated with the Fermat metric, and then you can define the forward ball and the backward balls. Here the difference is that you put here x here in the first place or in the second place. And then you can define also the symmetrized distance, which is obtained using dpq plus dqp. And well, it turns out that you can express the future, the chronological future and past of the stationary spacetime in terms of these balls. Basically, you can, in this picture, it's very clear. When you take the slice of height S, the intersection of this slice with the chronological future is just this ball here. Okay, it's just this ball, and it happens the same with the chronological past. So with this information, we can control the causality in terms of using this Fermat metric. Okay? So we have this theorem, which we characterized all the causal steps of the causal ladder. Well, the causal ladder is here to the right, and it turns out that the standard stationary spacetime is always causally continuous. Then it's causally simple if and only if the Finsler manifold is convex, and it is globally hyperbolic if and only if the intersection of the forward and backward balls are precompact for every x in S and every radius. Okay. Finally, a slice is a hypersurface if and only if the Fermat metric F on S is forward and backward complete. Okay, so well, what we can do many things. There are very interesting applications using this relation. Well, the first observation to get these applications to Brandeis metrics is that when you have a stationary spacetime, a standard stationary spacetime, you have a splitting. Okay, but you can change it. You can change the splitting. Okay, you can consider another splitting. Well, then it turns out that two Brandeis metrics are associated to the same splitting if and only if the difference is the differential of a function. Okay, is the differential of a function, and this function, this function which gives the differential, it is basically the graph of one splitting using the other. Okay, so if we have a splitting R times S, we can express the other splitting. I mean, the other splitting is obtained when a slice, the slice SF. And this slice, well, it's not a slice, it's a transversal hypersurface, a spatial hypersurface. This slice can be expressed like a graph in terms of S, okay, in terms of the first splitting using this function F. So this is the function that you have to put here. you have to put here is the different the function which you obtain the difference between the two Brandeis metrics. So, well, in some sense, you control, the family of Brandeis metrics associated with one standard stationary spacetime is very well controlled. Okay, it's very well controlled. And of course, when you, with the difference of these two Brandeis metrics is the differential function, this means that they have the same pregeodesics. Okay, here I've written the same geodesics, but in the title, but in fact it's the same pregeodesics because the parameterization is not the same. Okay, so we have a family here associated, an entire family of Brandeis metrics associated to a stationary spacetime with the different splittings. Okay, and all of them have the same pregeodesics. So we can obtain this very nice theorem, a generalization of Hopf-Ryu theorem. So there are several characterizations, but well, here RF is the initial Brandeis metric minus the differential function, and well, I'm going to focus on this characterization. The intersection of the balls are compact, and this is equivalent to the existence of a function f such that Rf is geodesically complete. So Rf has the same pregeodesics as R, okay, but it is geodesically complete. Moreover, this well, this condition here, this condition is very interesting because it hasn't appeared before in the Finsler world, but it's very interesting because, in particular, it implies the convexity of the Brandeis metric. Okay, so there are several applications of the one can say that we found these results using Lorentzian spacetimes. Okay, it is an application, a consequence of this relation between stationary spacetimes and Brandeis metric. There are many other, let's say, results that you can obtain, and you can describe Cauchy development using the Gabo-Fermat distance. You can give results about the differentiability of Cauchy horizons. You also can describe all the causal boundary of the stationary spacetime, which is done here in this paper by Flores, Herrera, and Sanchez, 2013. Well, you can give a lot of results about the existing multiplicity Moore theory of likely or periodic likely geodesics. And, well, this is also, let's say, a consequence of this interplay that I think that it was in this paper here. We proved that if you assume compact symmetrized balls, which is the same that the intersection of the backward and forward balls are precompact, then the Finsler manifold is convex. Okay, and this is very nice. Probably nobody thought that something like that could be possible because nobody tried to prove it before. Then we can try. Well, all of these results are very interesting, but all of them are for Brandeis metrics, except, well, this here, this the result of convexity, we proved it for an arbitrary Finsler manifold. But then the other result that we proved that is, if you have a Brandeis metric F such that the intersection of the forward and backward balls are precompact, then there exists this differential, this function F such that when you sum the differential of the function, you obtain a complete metric. Okay, this is done using the existence of smooth Cauchy hypersurfaces in a globally hyperbolic spacetime. So, well, how can you prove this in general for a Finsler metric? We precisely in this series of conferences in 2011, we discussed this with Vladimir Matev, And he obtained a direct proof of this for an arbitrary Finsler metric, okay, using on approximations of Lich's functions by smooth functions. Okay, but the point is that also by this time in 2012, it appeared a paper working with cone structures and proving that in a, let's say, globally hyperbolic cone structure, there exists a smooth Cauchy hypersurface. So using this result by Fatih and Skonoffi by the same period, you can prove the existence of this function, which in some sense you obtain a trivial change which is complete using Finsler spacetimes. In particular, you can use this class of Finsler spacetimes here. Okay, this class of Finsler spacetimes, which are called stationary Finsler metrics or static Finsler spacetimes, and then the result by Fatih and Skonoffi. This was done in fact, but Erasmo Caponio and Stancarone in this paper of 2016. But well, he uses they use the result by Matev, but you can do it also using with the same approach, but with basically what they do here is to characterize the causality of the standard static Finsler spacetime in terms of a Finsler metric. Okay, in this case, the Finsler metric is going to be arbitrary. So at the end, you reobtain the result by this result that was firstly obtained by Matev. Okay, so given a Finsler metric F, if the compact balls are, if the the intersection of forward and backward balls are compact, then there exists a function F such that F plus df is complete. Okay. Okay, so well, there are more results about causality. For example, Gibbons, Sergei Warpik, and Werner in 2009, they related constant factor to Brandeis Manifolds with some classical spacetimes. There are some extensions to the case in that you have a Killing vector field, but it's not time-like. Paper in collaboration with Erasmo Caponio and Miguel Sanchez. You can also consider a stationary spacetimes such that the slice is non-space-like. And in such a case, this is a paper in collaboration with Herrera, Jonathan Herrera, one of the organizers. And in this case, the Finsler metric, it is not positive. It is not positive. But it is very interesting because in such a way you can consider all the magnetic trajectories, because the magnetic trajectories are critical points of this functional here. I mean, of the length of this functional. But in this case, when you consider magnetic trajectories, omega is arbitrary. So, and this can be negative. Okay. So let's go now to the third part, semilunar navigation problem. And well, in order to explain semilunar navigation, just imagine that you have an object that in principle travels at a constant velocity in all the directions, but then there is a wind, it appears a wind, and well, the velocity is not anymore v, which is constant, has constant norm, but it's v plus the wind. So now the velocity is not the same in all the directions. Okay, there is an anisotropy. So we want to find the trajectory that minimizes the time. And for example, imagine that you want to cross this river, Amazon River, and well, there is a current, and you have a boat with an engine, which is it provides always the same velocity, but then there is the current. So which is the path here in the river, which is best, which is faster, which is the fastest path? Well, this is Cermelo problem. This is what a Cermelo problem tries to solve. Okay, it was proposed by Cermelo in 1931. There were many people working, but on it. But well, Zhongmin Shen in the beginning of 2000s proposed to study this problem using Finsler geometry. Okay, so let us see how to reduce the Zermelo problem to Finsler geometry. In principle, what we want to do is to minimize the time. Okay, so we have to compute the time. How can we compute the time? Well, the time, you know that velocity is equal to space over time. So time, the differential of time, is equal to the differential of the space over velocity. So which is just making the integral of this is we obtain this formula here. So, well, assume that the speed depends only on the direction. Okay, in such a case, we can define this hypersurface here. Well, in the case, if you have a wing, this hypersurface is obtained like this. Is the velocity plus the velocity without wing plus the wing. Okay, in this case, we are considering, well, velocities which are always the same norm without the wing. Okay, so basically, sigma is the translation of a sphere. Okay, of a certain radius. Sigma is the translation of a sphere. Then we know that the velocity is equal to lambda times gamma dot. It's proportional. I mean, is okay. The velocity it's proportional to gamma dot. We don't know exactly who is lambda, but we know that lambda times gamma dot belongs to the indicatrix. Okay, because the velocity belongs to the indicatrix by definition. Okay, then making this substitution here in this formula, we obtain that the time is equal to the integral of 1 over lambda. So who is lambda? Who is lambda? Let's see who is lambda. We know that we can define, recall, at the beginning, I said that a Minkowski norm is determined by the indicatrix. The indicatrix has to be strongly convex, has to be the curvature of this hypersurface has to be positive. Okay, and this is the case because it's the translation of a sphere. Okay, so I can construct a Finsler metric with this indicatrix, having as indicatrix sigma. Okay, so Z on lambda gamma dot is equal to 1 because I'm assuming the lambda gamma dot is equal to the velocity, and the velocity belongs to the indicatrix. So Z on the velocity is equal to 1. Okay, but using positive homogeneity, this lambda goes out, and then we obtain that Z on gamma dot is equal to 1 over lambda. So this is equal to Z on gamma dot. Basically, we have proved that the time is the length of gamma computed with a Finsler metric. Okay, is computed with a Finsler metric, and this metric can be computed explicitly in the case that our indicatrix is the translation of a sphere. More precisely, here what we know is that this quantity is a unit vector for G, for the initial Riemann metric. Why? Because look, this is here in this picture, this is V, this is the vector V. This vector here is V over ZV. And then you have here, this is minus W. And well, this is exactly this vector here. So this is in the indicatrix of G. This red circle is the indicatrix of G. So we have this relation here, and with this relation, we have a second degree equation in Z on V. Solving this equation, we can obtain the explicit expression for the Zermelo metric. Okay, so if we want to compute the trajectories of that minimize time in the presence of a wind, we have to consider this metric here and to compute geodesics. Okay. Okay. Well, in the case with strong wind, the point when the wind is very strong, the zero vector is not inside of the compact Story-Conver hypersurface. So there are some problems. You have to consider some generalizations. But in the case of space, in particular, spacetimes are very useful. Okay, because here the indicative does not contain here in this picture. The indicative does not contain the zero vector, but in the spacetime you have a Lilac cone, which is a normal Lilac cone. The only thing that here, this direction here is not pan-like. So we don't have a stationary spacetime, but we have we can construct a spacetime with Killing vector field, okay, which is associated to these metrics. Okay, but now I don't have time to speak in detail of these things. Basically, I don't have much time, so I prefer. How long do I have?
Yeah. Okay. Yeah, you have still -3 minutes.
-3.
Yeah. Okay.
I started. Okay. So let's finish with the application to wildfire spirit modeling. Basically, the Huygens principle says that the wavefront in time t is the convex halo of the sphere as of radio t. And well, then in an anisotropic media, you have to consider the indicatives of a Minkowski norm. And when the Minkowski norm changes from point to point, then you have to use the distance to the emitter wavefront. Okay. Well, if the wave emitter is a point, then you have to consider geodesic balls. Okay, this is done in this paper by Bennett Palmer. Then Steinbach-Borsen consider Finsler metrics to modelize these things, because well, the important thing here is the velocity, speed of the fire in every direction. And this speed depends on the wind, this depends on the slope of the surface and on the amount of fuel, the vegetation, and so on. So you can consider Zermelo metrics and Matsumoto metrics, okay, in order to make the prediction. Then you obtain a metric and you have to compute the geodesics of these metrics, okay. This was done here. This is very important because it can help in the strategies of prevention and where to put in the fireworks and so on. So, well, the point is that in the general case, you have to obtain, when you have a general wavefront, you have to compute you can apply the Zermelo problem, and you have to, you obtain the Zermelo metric given the velocity in every direction, depending on the slope, on the wind, and so on. You apply Huygens principle, and then given a wavefront, you obtain that the minimizers to a submanifold are geodesics orthogonal to this submanifold. So if you want to compute the wavefront, you have to basically you have to compute the orthogonal geodesics to the wavefront. Here there is a picture. This picture is in the second paper in collaboration with a PhD student, Enrique Pendastre-Condon and Miguel Sanchez. And well, here we have the wavefront, and then we compute the orthogonal geodesics to this wavefront. So we can compute the wavefront in a certain time. And this is very nice because it is very fast to compute. Okay, so I think that this is, I'm going to finish here, but the moral of the story is that you can even use a space-time to compute the wavefront of a wildfire, okay? Because you have to use a Zermelo metric. You can use a Zermelo metric computing the velocity in every direction, and then you can use a space-time that can be constructed from this Zermelo metric. Okay? And then at the end, you can construct the geodesic using a space. You can study this problem using a space. So I'm going to stop here.
Okay.
Thank you very much for your attention.